Oh, yeah, got it.
I think to our first in-person speaker, punctuality is probably not.
Yeah. There seems to be at least some so far. 1, 2, 3, 4, 5. Maybe like 5 at the moment. Yes, how many people are on the Zoom?
You feel ready?
Yep.
Okay, so we're gonna, okay, first of all, I'm very happy to have the return of the in-person colloquium. Yeah. Yeah, so thanks for coming. Thanks to you on Zoom if you can hear me, hopefully. And yeah, I'm really happy to have our visitor, Dr. Carolyn Reinhart here. Carolyn did her PhD at Iowa State under Leslie Hodgman. Carolyn is an expert in spectral graph theory and the inverse eigenvalue problem, and has done some work on like combinatorial games on graphs. And in particular, she is truly the expert on the distance matrix, and she's going to tell us about that today.
All right, thank you. Thank you for the introduction and for the invitation here. Just like this is your first in-person colloquium, this is my first in-person talk since the beginning of COVID, so I'm very excited to be here. Yeah, so I'm going to be telling you all about distance matrices today, in particular the normalized distance Laplacian, which is the matrix that I defined, and so I'm very excited to tell you about it, and also a little bit about the distance matrix on digraphs. So let's get started with some background and definitions. Let's see, there we go. So first, what is a graph for anyone who is not a graph theory person? Graphs are just a mathematical object, which can be used to model real world situations. So I like to tell anyone who's not familiar with a graph, just think about the internet, and you have edges that are connecting the vertices. Those are the links between websites. It's like a basic idea of what a graph is. And the internet is really, really large. So we would rather not think about all the connections of the internet. We don't want to write that down and look at it. So in order to study a graph more efficiently, we can encode it into a matrix, and that's what spectral graph theory is all about. So what is spectral graph theory? So spectral graph theory is the study of the properties of a graph in relation to the spectrum of a matrix representing that graph. And we define that matrix in various ways. There's a lot of different ways we can do it. This mathematical problem was first introduced in the 1950s, and it was introduced sort of simultaneously in several different papers, and focused on the study of what's called the adjacency matrix, which I'll be defining in a little bit. Independently, the energy of electrons was modeled using eigenvalues of graphs in a 1931 paper. And so this sort of tells you there's a lot of applications of spectral graph theory out there, and some of them sort of arose on their own. Graham and Pollock were the first ones to introduce the distance matrix. And they did so in order to study the problem of routing messages through a network. Back before we had our wonderful wireless network that we have right now, you had to actually connect telephone lines to each other. And so this was sort of helping with that. And then many variants have been introduced since, both just from a purely mathematical interest and also to tackle certain applications. And so today we're going to be talking about the distance matrix and its variants mostly. So some big questions in spectral graph theory. For matrix M, we want to know, can we bound the eigenvalues of the matrix? And in particular, the spectral radius of that matrix. We also want to know which families of graphs give us a tight bound on the spectral radius. We'll also want to know how often the spectrum fails to differentiate between graphs. So I'm going to be defining these things more in a little bit, but basically we want to be able to use the eigenvalues of the matrix to tell the difference between two graphs that aren't the same graph. And we want to know why this doesn't always work and when it doesn't work. Can we describe constructions that produce such graphs that fail to differentiate? And what properties do such graphs have to have in common? All right, so getting into some definitions here. A graph is a pair of vertices and edges, such that each edge is a pair of two vertices. And we are talking about a simple graph right now, so the edges aren't directional. If there's an edge from I to J, there's also an edge from J to I. And if there's an edge between two vertices, we say that those two vertices are adjacent. Also, the set of vertices that a certain vertex is adjacent to, we call its neighborhood. And the number of such vertices, or the size of the neighborhood, we're going to call the degree. Also, in graph theory, there's such thing as a path, which is just a sequence of edges between vertices. So this is the path on 5 vertices here on the screen. And the length of the path is the number of edges. And paths are very important in graph theory because we want to look at only graphs that are connected. And a connected graph is a graph where each pair of vertices has a path between them. This is going to be very important when we study distance matrices, because if we're looking at the distance between two vertices, if it's not a connected graph, we can't define the distance. All right, so here's an example of a disconnected graph. All right, and then a few matrix definitions, in case anyone isn't familiar. An eigenvalue is just a number such that if we have an eigenvector, that m times the eigenvector is equal to the eigenvalue times the eigenvector. We don't really need to know the mechanics of eigenvalues for this talk, but they're a really cool matrix property. The spectrum of a matrix is the set of eigenvalues, and the multiplicity is the number of times that eigenvalue appears in the spectrum. And then the characteristic polynomial of a matrix just gives us the eigenvalues. It's a polynomial where the eigenvalues are the roots of the polynomial. And so here's an example of a graph. We have this matrix A, which is actually the adjacency matrix. And then we have the eigenvalues, the spectrum, and the characteristic polynomial. All right, so today we're going to be focusing on matrices that are just real and symmetric. And so a symmetric matrix just means that the ijth entry and the jith entry are the same. And the reason why we want to think about real symmetric matrices, it makes life easy. They have real eigenvalues, and they have a basis of real orthonormal eigenvectors, which again, we don't really need to know the details of, but it makes everything work out nicely. All right, and so I mentioned at the beginning of the talk, one of the things that we like to study with spectral graph theory is the spectral radius. So the spectral radius is defined to be the maximum of the absolute value of the eigenvalues, but actually, the largest, or in our case, for the graphs that we're considering, which are Again, these are words you don't really need to know the meaning of, but irreducible non-negative matrices and positive semi-definite matrices. All of these matrices have the spectral radius equal to the largest eigenvalue. So when I'm talking about the spectral radius, I'm just going to be talking about the largest eigenvalue of the graph. All right, so now I'm going to start showing you some actual matrices that you can use to study spectral graph theory. So the original matrix is the adjacency matrix, and it's exactly what you would expect it to be. We put ones where we have an edge, and we put zeros where we don't have an edge, right? So we're keeping track of the adjacencies of the graph. So here's the adjacency matrix of this little example graph, the PA graph it's called. This is my favorite little example matrix, so you'll be seeing it a lot. We can also define some Laplacian matrices. So if we let D be the matrix where the diagonal is degrees, then we can define two Laplacians. One is called the combinatorial Laplacian, and one is called the signless Laplacian. And those are the degree matrix minus the adjacency and the degree matrix plus the adjacency matrix. And the reason why these are really cool, if you look at the example, you'll notice that the sum of the rows on the combinatorial Laplacian is 0, right? That's a really cool property. And so another thing that we can do from here, or that people have done, is want to normalize these. So the downside to the Laplacian matrices is that the eigenvalues can get really, really big. They're not bounded nicely. But if we normalize them, then we get the normalized Laplacian matrix. And this matrix is really nice because its eigenvalues are nicely bounded between 0 and 2. We'll talk about that in a little bit. All right, so this was first defined by Fan Chung, and we can observe that the normalized Laplacian is the Laplacian matrix, the combinatorial Laplacian, multiplied on both sides by this degree matrix to the -1/2. All right. So I told you about all those matrices, and I did that because we're about to start talking about distance matrices, and we're going to take a very parallel path, a very parallel approach. Oh, first, here's your example of the normalized Laplacian. So it looks a little messy, but it has nice properties. All right, so I've been saying the word distance a lot. What is the distance between two vertices? It's the number of, it's the length of the shortest path, or the number of edges of the shortest path, right? So the distance between vertex 1 and 4 is 2. And we can also define what's called the transmission. And the transmission is the sum of the distances from a vertex to all the other vertices. So you can sort of think of it as like analogous to the degree when you're talking about adjacency, right? The adjacency, when you add up all the adjacencies, you get the degree. Here we're adding up all of the distances and we get the transmission. All right, and now we can define we can also define the transmission matrix to be the matrix with diagonal being the transmissions. So the distance matrix, which I've been talking about, is just the matrix where the entries are the distances. So this is a generalization of the adjacency matrix, right? We have the adjacency matrix encoded in there, but now we care about more than just the adjacencies. We also care about how far apart all the other vertices are. So here's an example of the distance matrix for the PA graph. And so then we can analogously define the distance Laplacian and the distance signless Laplacian, which before we had the degree matrix minus the adjacency matrix for the Laplacian. Now for the distance Laplacian, we have the transmission matrix minus the distance matrix. So this is analogously defined. It makes a lot of sense that we would define this kind of graph. right? So here are examples. Note that for the distance Laplacian, we still have that nice property where the row sum is 0. And so then it's only natural to wonder, what about the normalized distance Laplacian, right? So that is what I did in my dissertation work, is I defined the normalized distance Laplacian matrix. And here's the definition of it. It looks horribly messy, but the entries are negative of the distance over the square root of the transmissions. And that's analogously defined to the normalized Laplacian. But you can see it has that property just like the normalized Laplacian, the diagonal is 1s, right? And we're going to actually see that it has a lot of similar properties, but not all the same properties. It's a little bit different. All right. So we can see that it's defined in the same way in relation to the Laplacian matrices in the distance matrix. And in particular, if we had a graph that was transmission regular, which means that all of the transmissions are equal to a certain k, right? Normally, we might talk about a regular graph, which means all of the degrees are a certain k. But here we're going to talk about a transmission regular graph. So all of the transmissions are that k. And in that case, all of the eigenvalues of the distance matrices are just translations of each other. You can multiply by a scalar and you can add a scalar, and you'll get the different eigenvalues. So that's a nice relationship that we have between the distance matrices. All right, so one of the tools that we're going to use to compare the normalized distance Laplacian matrix back to the regular normalized Laplacian is using weighted graphs. So a weighted graph is just a graph where we add a weight. In this case, I'm doing weights on edges. We add a weight to each edge. And then the degree of a vertex is just the sum of the weights, right? So here, this vertex on the top left, we would add 758 plus 5, right? And that would give us our degree. And we can make any unweighted graph into a weighted graph by just assigning a weight of 1 to every edge, right? So let's define a graph where we take a complete graph and we add the edge weights that are equal to the distances between the vertices in our original graph. So what do I mean by that? If you see here, vertex 1 wasn't adjacent to vertex 4. They had distance 2. But now there's an edge between 1 and 4 with a weight of 2, right? And we can see that in our weighted complete graph, the graph on the right, we can see that the degree of a vertex is equal to the transmission of that vertex, because we're just summing up all of the distances. All right, so what that allows us to do is it allows us to determine that the normalized distance Laplacian of a graph is equal to the normalized Laplacian of that weighted complete graph. So anything that we know about a weighted complete graph for the normalized Laplacian, we can just port over. So there's this nice theorem from Van Chung, which bounds the eigenvalues of weighted complete graphs. It says that all the eigenvalues are between 0 and 2. And in fact, the largest eigenvalue is equal to 2 if and only if the graph is non-trivial and bipartite. So a bipartite graph is just a graph where you can draw all of the vertices and so that they're in 2 sections, right? So you've got some vertices over here and some over here, and the edges only go between, they're not inside of these, right? So if we have this, A complete graph is just a graph where all the vertices are connected. All the vertices are connected to all the other graphs. So this is clearly not a complete graph because we know that the vertices in here are not connected to each other. So if only bipartite graphs have the largest eigenvalue equal to 2, then we can't have a graph with largest eigenvalue equal to 2 for the normalized distance Laplacian, because those are only weighted complete graphs. So notably here, we have the same bounds, except that this upper bound cannot be tight. There's no graph with largest eigenvalue equal to 2 for the normalized distance Laplacian. So that leads us to ask the question, how big can we get, and what graph might achieve that? So we know that the largest eigenvalue is 2, as we just said, if and only if it's bipartite. We also can say that for the other distance matrices, so the distance matrix, the distance Laplacian, and the distance signless Laplacian, the spectral radius maximum is achieved by the path graph, which is just all the vertices in a line, right? But that's not true here either. So there's this sort of weird behavior going on. If we don't have a bipartite graph, we don't have a path graph, what is it? What graph can we maximize with? So the answer is we don't know, but what I'm going to show you next is the family that I conjecture to be the maximum. And I can show you some of my reasons why I conjecture that. So we can find the family which we have a complete graph, which is, again, a bunch of vertices connected, another complete graph, and then we have a path between them, right? So it looks like this graph here on the screen. And when we get really, really big, right, we're going to have these big clusters of vertices and then a single line of vertices in between them. All right, so here is my data for graphs with high spectral radius. These ones, this data for 1 or 2 through 10, excuse me, those are graphs that I know are the graph with the largest spectral radius on that number of vertices. So up to 10, I can tell you this graph is the graph with largest spectral radius. And here is what its spectral radius is. It's interesting that it's not very large. It's only, 1.6-ish. When we get big, it slowly starts to move in the direction of 2. These on this side are not necessarily, I'm not telling you these are the best, but they're the best I could find by searching this family that I conjecture. So note that when we get really, really big, the complete graphs, these are the size of the complete graphs, the ones on the left and numbers on the left and right, they get really big compared to the path, right? So it's sort of like, but the path isn't like tiny, it's not 2 vertices, but it's sort of this like medium, like smallish number. So I'm very perplexed by this. I think Mike is also perplexed by this, but this is something that I would love to see solved. So my conjecture specifically is that there's some family of graphs, some ratio of n's in here, such that this family both approaches 2 as n approaches infinity in spectral radius, and that it's the largest such one. All right. So moving on to a little bit of a different topic, I mentioned at the beginning, another thing that we care about in spectral graph theory is this failure to distinguish between 2 graphs that are not the same graph, right? So 2 non-isomorphic graphs, right? They're not the same. They don't have an isomorphism between them. We call them cospectral if they have the same eigenvalues, even though they're not isomorphic, right? It's clear that if 2 graphs are isomorphic, they have to have the same eigenvalues. But the other way, you know, in a perfect world, there would be no cospectrality, and we would have found the way to always distinguish between graphs, right? But that's not going to happen. So what we want to do is we want to study this case of like failure. So the number of graphs where that happens has been computed for these different matrices on 10 and fewer vertices. The only graph that it hasn't been computed on 10 vertices is the normalized Laplacian. It gets computationally difficult because you have a lot of graphs. The reason that I was able to compute it for the normalized distance Laplacian and not the normalized Laplacian is because for the distance matrices, remember, we only consider connected graphs. And the adjacency on all of its Laplacians, we consider all graphs. So there are many more graphs to check. So here we can see, though, by looking at these, that there are very few graphs that are cospectral for the normalized distance Laplacian in comparison to the other distance matrices. And, you know, somewhat in comparison to the other matrices, although again, it's a little hard to compare this top row and the bottom row because we're looking at a different set of graphs, right? But you can see here, we don't have anything happening until 8, and then it's only 2 and this 2 means it's one pair of graphs, right? And the 8 in this case actually means it's 4 pairs of graphs, right? Sometimes you can have multiple, like it can be a set of like 3 or more graphs that are isomorphic. So that's why the numbers are reported this way. But in this case, it's 1 pair and 4 pairs. There are a few triples in that 7,000, but it's mostly pairs again. All right, so at this point, usually someone says, show me a graph. So I'll do that in a second, I promise. But here's some percentages for you, which maybe make it a little more clear. So all of these, you know, it's 5%. I guess this is 0.3%. But here we have 0.01, 0.003, 0.06. So these are just a very small percentage-wise. All right, so here's some graphs, as I promised. So this is our only pair of cospectral graphs on 8 vertices. And I've highlighted for you the edge that is different between them. So this is the only edge that's different between them. And you can actually see that these vertices are the same. The vertices 3 and 4 and the vertices 1 and 2 are the same except for, like, their neighborhoods are the same, right? So they have all the same neighbors as each other. And that's what we call twins in graph theory. And so this is sort of a well-known construction method that you can use to find cospectral graphs. But it doesn't always work for the normalized distance Laplacian. There are other matrices where it always works to add a vertex between two different pairs of twins. But here it's not guaranteed to work, but that is sort of explaining what's happening here, which is interesting. This is 3 different pairs of vertices on 9, or cospectral graphs on 9 vertices, where you include 0 dashed edges, 1 dashed edge, or 2 dashed edges, right? The dashed edges are sort of optional. And again, we're sort of doing this toggling of an edge, right? We either add an edge between 3 and 4, or we add an edge between 1 and 2. And in this case, these vertices, if we have some of the dashed edges, aren't necessarily twins, but they're this other graph thing called cousins, where they're close to twins. They're like almost twins, but they're a little bit off. I don't know why. We should have really called them siblings in that paper, but for some reason we landed on cousins. So again, this this pair of graphs, or actually 3 pairs of graphs, can be explained by a known cospectrality phenomena. But again, it doesn't always work, right? This is an instance of cousins producing cospectral graphs, but you can't always find cousins and get cospectral graphs for the normalized distance Laplacian. There's some condition we're missing. And then if you thought all of the cospectral constructions were nice and we were just toggling edges, sorry, we have this weird graph right here where we have actually a different number of edges even. So the one on the right, we add 2 extra edges. So this is the last pair on 9 vertices. All right, so one of the other questions we can ask, so before I move on, let me say, I sort of sneakily was talking about some more open questions in here. So I don't know how to constrain this like cousin construction to find an actual construction for the normalized distance Laplacian, and that's something that I would love to do in the future. So another thing that we care about with cospectrality is what's called preservation of parameters. So if we have 2 graphs that are cospectral, we say a parameter is preserved if those 2 graphs have to share the same value for that parameter, whether it be like numeric or true false. So it's pretty easy to see that the number of vertices in a graph has to be preserved, because if we have the number of vertices determines the size of the matrix, which then in turn determines how many eigenvalues you have, right? So if you have a set of eigenvalues where there's 8 of them and a set where there's 9 of them, they can't be cospectral. So also, this example shows us something. This example shows us that the number of edges is not preserved, right? So the number of vertices was preserved by cospectrality. The number of edges is not. We found an example where these 2 graphs are cospectral, but they have a different number of edges. So here is a collection of information that we know about what parameters are preserved by cospectrality for different matrices. So what's really interesting is the yeses, right? We have that, so the Wiener index is just some specific index in graph theory, and it's preserved by the Laplacians. We also know that the distance Laplacian preserves the transmission regularity, right? And that the signless distance Laplacian preserves the transmission regularity, and the distance Laplacian preserves the number of connected components in a graph. And so this is sort of a collection of everything that's known about some of these parameters that people care about in graph theory, whether they're preserved or not. I recently wrote a survey with my advisor, Leslie Hogben, and on distance matrices, and we sort of compiled this and filled in a bunch of the blanks. We were looking for a yes, but instead we found a bunch of no's, but at least the chart got a little more filled in. So I just wanted to show some examples here. So the complement of a graph is just the graph where you take all of the edges that aren't in the original graph. And here is the examples which show us that the complement is not preserved for anything except for the distance Laplacian. So here's the graph complement, and then the other graph and the other graph complement. Notice that this is the Peterson graph, which I thought was interesting. All right. So another sort of tool that we use in graph theory, in linear algebra when we're talking about eigenvalues, is the characteristic polynomial. And I sort of mentioned that at the beginning. And if we want to think of a way to unite the characteristic polynomials of all of these matrices that we care about, we can look at something called the generalized characteristic polynomial. And that basically allows us to consider actually all of the different, the adjacency matrix and its Laplacians all together. Basically, this characteristic polynomial, if it's equal for two different graphs, then those two graphs are adjacent for all four of those vertices, all four of those matrices, right? So I defined the distance generalized characteristic polynomial, which is defined very analogously. And we know we can show that if this characteristic polynomial is equal for two different graphs, then those two graphs are cospectral for all of the distance matrices. And one of the ways that we can use this idea is we can actually use it to show something that's, we can use it to show something else about those graphs. So here, we know that for the standard generalized characteristic polynomial, two graphs have the same degree sequence if they had the same generalized characteristic polynomial. And an analogous thing holds true for the distance generalized characteristic polynomial. So I was able to show that those two graphs have the same transmission sequence, which is just the set of transmissions in the graph, right? So it's just like a variable in your characteristic polynomial. Yeah, it can be anything. Yeah. And so then this tells you that if your graphs are cospectral for all of the distance matrices, actually the DQ should be in here too, then they have to have the same transmission sequence. So this is sort of like those parameters that are preserved, but this is like, if they're cospectral for all of them, all of the distance matrices, then they have the same transmission sequence. All right. So the last thing that I want to talk about is like different topic. And this is talking about the distance matrix defined on digraphs. So before we were talking about graphs that have edges that go both directions, right? So if you have an edge over here and an edge over here, it goes both, or sorry, vertices, the edge goes between both vertices. But here, edges now we have direction. So a digraph is a set of vertices and a set of edges that, a set E that we actually call arcs now instead of edges. And each arc is an ordered pair of vertices. So we can see here, we can put arrows to denote the direction, and an edge can go both directions, but it doesn't have to. We can put an edge just in one direction. And just like with regular or simple graphs, when we wanted to study distance matrices, we needed connectivity. We needed to get between all of the vertices in the graph. So here we need something that's called a strongly connected digraph. So if we want to get between the vertices in the graph, we need there to exist a path from U to V for all of U and V, right? And that specifically is directional now. So the graph on the left is not strongly connected because if we go from this vertex in the middle to the vertex on the right, we can't go back. But the graph on the right is strongly connected because now we can go back. So an arc in a digraph is a doubly directed if it goes both directions. And a doubly directed digraph is just a graph where all of the edges go both directions. And then it might as well just be a graph, right? And just like with simple graphs, we think about neighbors, but now we have to think about in neighbors and out neighbors. An in neighbor is a vertex where you are going from U to V, and an out neighbor is the reverse. And we can define the distance in an analogous way, but now again, distance is directional. So the distance from U to V, not just the distance between U and V. And so we get this distance matrix, where again, all the entries are distances, but I want you to notice that it's not symmetric, right? So on the top right corner of our matrix, the 1, 4, this is a distance 2, but then 4, 1 has a distance of 1, right? So we lost all of our nice things that we get from being symmetric, right? That doesn't make us very happy. So not much has been done in terms of, most of what's been done in terms of digraphs for spectral graph theory digraphs. Most of what's been done is in the realm of the spectral radius, because there are some techniques that we can still use that are like nice and don't get too messed up. But with a lot of our proofs for spectral graph theory in the cospectrality realm, a lot of it revolves around like eigenvectors, and we don't get a nice set of eigenvectors anymore. We lost that when we threw symmetry out the window. So it can be a little tricky to talk about to prove some of these results. So just like with simple graphs, we can define two digraphs to be cospectral for the distance matrix if they have the same distance spectrum. And we can observe right at the gate that if we have a digraph and we reverse the arcs of it, so you can see on the left, you reverse the arcs and you get the one on the right. So for example, this top arc goes to the right and then it goes to the left. So we're flipping all the arcs. What we're ending up with is basically the distance matrix that's just the transpose of the original distance matrix. And these two matrices have the same eigenvalues. So this accounts for like a huge number of digraphs that are cospectral for the distance matrix. Interestingly enough, this doesn't happen with the other distance matrices of digraphs, like the Laplacians, but it does for the distance matrix. So here's the number of digraphs with distance cospectral mates. So so the normalized distance Laplacian was cool because it had very few cospectral graphs, cospectral mates. The distance matrix for digraphs has tons of cospectral mates. If you look here, now we're on a smaller number of vertices because there are way more digraphs than there are graphs. But you can see that there are tons of graphs with cospectral mates. In fact, like almost all of them. And not even as many as you would expect are accounted for by this arc reversal. So here's the percentage with a cospectral mate, and here's the percentage that are not just from that arc reversal. We can also look at comparing to the distance matrix on graphs. It's a little bit weird because again, we're looking at a different n, right? Here is n 4, 5, and 6. And then down below, we can look at n 7, 8, 9. So it's a little difficult to compare, but we can see that the percentage of graphs with a cospectral mate is like in the 2 to 12% range. It's not like 50% like here. So it's a very different thing happening. All right, so as I already mentioned a little bit, unlike graphs, the distance matrix is not symmetric, not necessarily, and so all of our nice eigenvector things go out the window. So we have to focus on the characteristic polynomial of the matrix. And if we can show that the characteristic polynomial of the two matrices are the same, then we've proven that they're cospectral. They have the same characteristic polynomial with the same roots. So in a digraph, a loop is just an arc from a vertex to itself. This is a little loop on V. We're not looking at digraphs with loops in our general set, but we're going to use these loops as a tool to talk about how to prove two digraphs are cospectral. So this is like a scary matrix, a scary sum of products, and we don't need to get into the details of it. But basically, this is just a definition of the determinant of a matrix. And we can choose a specific digraph such that we have an arc where we have a non-zero entry in our matrix, which actually, in the case of a distance matrix, means we're going to have all the possible arcs. And so we're going to take these arcs and we're going to think about them as what's called the generalized cycle decomposition. So what is a generalized cycle decomposition? It's basically just, let's take all the vertices in the graph and let's put them into cycles that are either, like, they can be single loops or they can be longer cycles. And in this case, we count going from a vertex to another one and back. That's just like it's like a 2 cycle, right? In a simple graph, we would think about a cycle including at least 3 vertices, but here we can have a 2 cycle. So this is one cycle decomposition of the graph on the left. And the reason why we care about a generalized cycle decomposition of a digraph is because we can use it to compute the characteristic polynomial of that digraph. So if that matrix has, since our distance matrix has no 0 entries, well, since our distance matrix with subtracted from xin, because we're looking at the characteristic polynomial, and we calculate the characteristic polynomial by doing x times the identity matrix minus the distance. So since this has no 0 entries, we want to look at the complete digraph with loops on every vertices, on every vertex. So all of the arcs you can possibly have. And we can set up, we want to let L be the number of loops and capital C be the number of arcs and E be the number of cycles. I mean, I don't want to get too much into the details here, but we can write basically a formula. Let's just look at this from a broad picture. This is how you compute the characteristic polynomial of a digraph for the distance matrix, given its generalized cycle decomposition. And so using that, we can make a cospectral construction. And this is one example of how we can do the cospectral construction. Basically, if we have a vertex U and a vertex W, whose neighborhoods might intersect but don't necessarily overlap, and then you take a vertex V, which has an edge from their intersection, and you add an edge to either U or to W, right? Then these two graphs, where you add either the blue edge or the red edge, these two graphs are cospectral digraphs. So this is just one example of this construction. I think I'm out of time, so I'm not going to go into the details of it. But we can, here's the actual statement of the construction. Well, no, the construction was on here, all the rules that you need. But basically, what we end up doing is looking at the different forms of cycle decomposition. So we either have one big cycle, we can have a big cycle, and we can have a smaller cycle. We can have like these loops hanging out. And basically, these are the cases that aren't just like the same for both of those graphs. And we can show that they contribute the same thing on to each of the characteristic polynomials. But anyways, I know that I'm out of time. So I like to end my talks with a more interesting picture than my math in case anyone's bored. So thank you, here's a cute puppy. Yeah.
I have 2 questions. if that's okay.
Yeah.
So I'm not an expert in spectral graphics, but I know that a lot of influence is given to the spectral radius. For distance matrix, spectral radius, is that the distance of the graph, or the maximum distance among any vertices, or is there some kind of relationship there?
So it can be.
It can't be. It seems, I was looking at the results, and it seems like it might be something.
Yeah, yeah.
Okay. And then
It's bounded by that.
it's bounded by that.
Yeah.
And you have this definition about 2 graphs that are preserved by cospectrality. And so they have specific parameters. Have number of columns been looked at? Or do 2 cospectral graphs have the same number of columns or a fixed number of columns?
Not that I know of, but that's a really interesting idea.
I'm into columns.
Yeah, yeah.
Just curious.
I don't know of anyone who's done that, but it would be interesting to see if there's like a relationship there. Yeah. Cool. Yeah.
Right.
Yeah.
I'm kind of curious how you actually, or how one actually counts the number of cospectral pairs of, say, graphs with 10 vertices.
Yeah.
I thought about calling them siblings, and then siblings. So mates was good though.
Yeah.
Mates.
Yeah.
Anyway, how do you go about counting that there's like, whatever, like,
Yeah.
cospectral pairs?
Yeah, so I used Sage, which is a Python-based language with graph theory built in. And, there's a bunch of different ways you can do it, but the most clear one is just to compute the characteristic polynomial and then subtract them and see if you get 0, right? That's computationally sort of long. Because then you also have to store a bunch of characteristic polynomials, right? You would have to basically make a list of all the characteristic polynomials and then compare them all to each other. But what you need to do when you have like a lot, like on 10 vertices, you need to be a little bit clever. What I did is I first did an initial sort where I evaluated the characteristic polynomial at like some random number and basically like sorted things that could potentially be cospectral into groups and then checked among those. And it takes a very long time. I think I had code running for over a week to do the 10 vertices on the normalized distance Laplacian. And that's with that like sort of clever, I think I actually sorted them like multiple times. So like I whittled the groups into smaller and smaller groups by just like evaluating the characteristic polynomial at different numbers. Yeah.
Your instruction about the complete graphs, do you have any relationship with the size of that graph?
Yeah, I don't have a specific ratio in mind, but I do think that the size of the path is like quite small and like relatively, but I don't have a specific ratio that I like conjecture or anything.
That's a risk.
Yeah, it's just based on some like sample data I've computed, but not. Yeah, no, go ahead.
I also noticed that there's big graphs and it was balanced.
Yes.
And then wondering, because I think I recall we had an extreme phase with point balance with very small numbers.
Yeah, yeah.
So are roughly the different sides that this really comes down.
Yeah, so again, this is just sort of like the data I've looked at, but as soon as you go like really unbalanced, like it's just not anywhere close to as large as it could be, in my experience. You know, I computed ones for the large numbers. I intentionally computed ones where I could balance the ends, right? I computed like, but you don't have, they don't have to be perfectly balanced, but they should be close, in my experience.
November 18th, which is also a Thursday.